In the previous video, we discussed how the rules of probability, and specifically some assumptions about the AND rule, the multiplication rule, relates to a chi-squared test. So the formal AND rule, the formal multiplication rule of probability, says that the probability of A and B, or bread and soup, is the probability of A times the probability of B, given that this already happened, given that A already happened. And so we get a number from that. And when we apply the formal rule of probability, we get a number that exactly matches the result we would get just straight from the data. So there's our bread and soup, and divide that by the 60 days we could have had bread and soup, we get 0.15. And if we run that through our longer equation with this, what's called a conditional probability, so the probability of soup conditional on the fact that we have already had bread, then we get the same number. So it's good that our rules of probability work. There's a simplified version, though, if we can make the assumption that the probability of soup is not conditional on bread. So this term is still real, but we're saying that, well, the probability of soup does not depend on bread, so we can ignore the bread component. And that's written out here, that the probability of soup given bread, assuming independence. That's kind of the big assumption here, that assuming the probability of soup is independent from the probability of bread, then this reduces down to just the probability of soup. And under that assumption of independence, we can rewrite this formal equation a little more simply and say that the probability of A and B, the probability of bread and soup, is equal to the probability of A, bread, times the probability of soup, B. And notice we don't have that conditional part because we are assuming, in this case, that bread is independent from soup, or that soup is independent from bread. When we calculate these numbers, we see that under the assumption of independence, we get an 11% probability, and that 11% is different than the probability we get when we do not assume independence. So immediately that would kind of suggest, well, the assumption of independence doesn't hold, because we know this is true, because that's what our data says. That number matches this number, and it does not match this. So our assumption of independence is not correct. However, all of these numbers were based on this one sample, and if we were to take a new sample of data, then it's possible that these would match, or at least they would get closer. And so we can ask, and should ask ourselves, in the long run, if we had lots of samples, would we expect these numbers to be about the same? And that the other way of asking that question, really the perhaps more important question, is, in the long run, is there an interaction between the data? So do we have to worry about soup being conditioned on bread, or are they independent? And so a chi-squared test answers that for us. In this particular data set, we have one row of data here. There are lots of rows, one column of variables there. And we have two variables. So we can see some chi-squared tests that just look like this. So there's a column that has our starches in this case, and just one variable. And in order to conduct a chi-squared test, we would need the expected values. These are all observed, so we need expected values. And so we would put another column here and somehow come up with what we think the probability of noodles should be, or what the count of noodles should be, and what we think the count of rice should be, and what we think the count of bread would be. In this particular case, we have no particular reason to assume that any particular number of days should be noodle days or rice days or bread days. We can't calculate an expected value that way. So it's fortunate then that when we have this row of options here and at least two columns of options here, that we don't calculate the expected value that way. We calculate it a different way. Ultimately, when it comes time to calculate the chi-squared, we'll run it through the same equation, but in order to come up with the expected value, the E here, we have to do it differently. So the way that was demonstrated in class without explanation was at the intersection of noodles and soup, we take the soup and we multiply that by the noodles. So we take the column sum and multiply it by the row sum. And then we divide that by the total, the grand total. And that is our expected count, the expected number of noodle soup days. And we can see that 9.6 is actually pretty darn close to our 10. We do not round this, by the way. It is perfectly legitimate to have expected values with decimals in them. Since our original data are counts, these cannot have decimals, otherwise it would not be a count, but our expected values, that is okay. For practice, let's just go fill in the rest of the table. So our noodle salad intersection means we take the salad, so our column total, times the row total, the noodles, and we divide that by the grand total. I see 10.3, well, that's also pretty close to 10. And we just keep on doing this. So there's our our column times our row divided by the grand total. Column times row divided by grand total. Column times row divided by grand total. And lastly, column times row divided by grand total. That's something that I certainly do and would recommend you do also, is take a look at the numbers you just calculated and briefly compare them just by eye to the original data. They're probably going to be somewhere close, and if they're really weird, then check your math and make sure that nothing went astray. In this case, everything's kind of the same order of magnitude, so we're off by a handful in some cases, 6 to 9 and 7 to 5, but that's to be expected, so it doesn't look like I made any math errors. So when it comes to the chi-squared, that is the formula that I told you to use, but I didn't explain why that should work. And there is a reason why we do it this way. It's actually a bit of a shortcut. Ultimately, we want to calculate an expected value given the empirical probabilities from the table. So we want to calculate an empirical probability for each of these cells. So let's go start with our noodles and soup. So what would the expected probability be for getting noodles and soup? Well, we have our empirical probability equation here. It's the same as when we were calculating all these guys. We have the number of things that we care about, and we're going to divide it by a total. However, in this case, we don't want the actual number of things. We want kind of a hypothetical number of things, an expected number of things. So we do this calculation purely on the marginals. Remember, the marginals are the numbers in the margins, the sum of columns and rows, respectively. So the probability of, let's just say the probability of soup, of any kind of soup, would be equal to 29. Let's do it this way so it doesn't turn into a real equation. It's equal to 29, so that's our total number of days, that's x, divided by 60. So those are the number of days when we could have had soup. So that is our empirical probability for soup. That's the same thing that we calculated up here, no particular difference. But that's in probabilities, and the chi-squared needs a count. So now we have to take this probability and convert it into a count. Well, we keep using our same equation. There's our probability, and we want a count. We want x, so we need n. Well, we're interested in the soup noodle. We've already accounted for soup, so n is the total number of noodle days that we could have had soup on. So if we rearrange this, we get our empirical probability. I'll just do empirical probability. We want x, so we need to multiply times n, and that gives us x. So this is the first part of what we did. This was our probability of soup. That's our EP, our empirical probability. And then we need to multiply times n, which is the number of noodle days, which is 20. So if we take that same thing and we just get rid of the apostrophe so it actually calculates that for us, we get 9.667, which is the exact same thing as we got just using this times that divided by that. In the way I'm doing it here, we're actually taking this divided by that times that. Ultimately, it's the same, it does the same thing, the same numbers, order of operations requires that. But that is the reason why we take the column sum times the row sum divided by the total. Ultimately, we're calculating an empirical probability, and then we're multiplying it by a total to convert that empirical probability into an expected count, because the chi-square test needs a count. So hopefully that made sense. Again, it was not talked about in class because it is not necessary to know that is where it was coming from. But there's a very direct relationship between our frequency tables and our empirical probabilities and how a chi-squared test works. Now we have our observed values, we have our expected values. We would run that through our chi-squared equation of taking our observed minus our expected and then squaring that and divide by our expected here. And do the same thing for all of these cells and add them up and see how big that number is. And then ask Excel to calculate the probability of seeing a number that large or larger. And if the probability is very small, then these two are probably never going to match. And we are, in fact, violating the assumption of independence between our starch and our side dish overall. I think that's it for that.